Hi everyone, welcome to our discussion in calculus. In this video, I will be discussing about the continuity of functions. Continuity meaning there are no abrupt changes, breaks, or jumps in our function. Now for this video, it will be divided into two parts. So there will be two parts. The first one is continuity at a point. And for the second one, we will be having continuity on an interval. So let's go. So for the first part, again, continuity at a point. As we have observed in our discussion of limits in topic 1.1 and 1.2, there are functions whose limits are not equal to the function value at x is equal to c. So I don't know if you still remember this one, but we talked about this before. That there are times that the limit of the function as x approaches c is not equal to f of c, meaning the limit is different when you substitute the value of c right away to our function. Now, this leads us to study of the continuity of functions. So in this section, we will be focusing on the continuity of a function at a specific point. Okay. So for limits and continuity at a point, so what does continuity at a point mean? Intuitively, so let me just read. This means that in drawing the graph, so if you're given the graph of a function, the point in question will be traversed. Traversed meaning the graph will be continuous. There will be no breaks. Again, there are no gaps. There are no jumps. So if it's a line, so it's continuous. If it's a parabola, so again, it's continuous, can be facing upward or downward. As long as it can be traversed, it is continuous in nature. So we start by graphically illustrating what it means to be continuity at a point. So example 1, take a look at this graph right here. So consider the graph below. This is the graph of f of x is equal to 3x minus 1. That's the graph of the function. Now the question is this function continuous at x is equal to 1? So for our solution or explanation or our answer, to check if the graph is continuous at x is equal to 1, so let's use the given graph. So again, take a look at the graph. Note that 1 is able to trace the graph from the left side of the number x is equal to 1 going to the right side of x is equal to 1. So here from the left going to the right side of the graph. So we are able to traverse, meaning the graph is continuous. 1 is here, right? So going to the right side without lifting one's pen. So you need not lift your pen because the graph is continuous. Okay, let me just erase these. So again, from the left going to the right side, it passes through 1, it traverses through 1. You need not lift your pen because the graph is continuous. So this is the case here. Hence, we can say that the function is continuous at x is equal to 1. So that easy. So next example, example 2. Consider the graph of the function g of x below. So take a look at this graph. This is the graph of the function. Y of x is equal to 3x squared minus 4x plus 1 over x minus 1. So take a look at this graph. Try to compare that with the graph earlier. So as you can see here, our point is included, meaning that's shaded. We're in here, it's not shaded at this certain point 1. So there's a certain difference. So still the same question. Is the function continuous at x is equal to 1? So for the answer, we follow the process in the previous example. So tracing the graph from the left of x is equal to 1. So from the left going to the right of x is equal to 1, one finds that he or she must lift his or her pen briefly upon reaching this certain point right here, creating the hole in the graph. So to draw the graph, you need to lift your pen because you need to create that hole right there. Then you continue with your graph. So thus this function is discontinuous at x is equal to 1 because at this certain point right here, that is not included in the domain of the function. Why? Let me erase this one first. Why? Because if you take a look at our function, take a look at the denominator, x minus 1. If in the case that x will be equal to 1, our function will be undefined, meaning at 1, x is equal to 1, our function is not defined. So that's not included in the domain, meaning the function is discontinuous at x is equal to 1. I hope that's clear. Example number 3. So consider the graph of the function h of x is equal to 1 over x. So we have here the graph of that certain function. And the question is the function continuous at x is equal to 0? What do you think? So for our solution, for our answer, if we trace the graph from the left of, wait, so if we trace the graph from the left of x is equal to 0, going to the right of x is equal to 0, we have to lift our pen. Since at the left of x is equal to 0, the values will go downward indefinitely, while at the right of x is equal to 0, the function values will go to upward indefinitely. So if you draw this graph right here, you need to lift your pen so that we can draw the other part of the graph on top. In other words, the limit of the function 1 over x as x approaches 0 from the left is negative infinity. Why? Because it's going downward indefinitely. But take note, it will never touch 0. It will just get closer and closer and closer to 0. Same with the graph on top. That's getting closer and closer to 0 there, but it will never touch 0. So it's increasing indefinitely. On the other hand, the one below is decreasing indefinitely. So for the left side of the function, the limit is negative infinity. For the right side, it's infinity or simply positive infinity. Thus, the function is discontinuous at x is equal to 0. Okay. So the concept there is as long as you need to lift your pen, as long as the graph is not continuous, meaning it's discontinuous at that certain point. Okay. So example 4. Let's use the same graph. Consider again the graph of the function h of x is equal to 1 over x. Same graph earlier. The question is the function continuous at x is equal to 2? So that's the question. So solution, if we trace the graph of the function h of x is equal to 1 over x from the left of x is equal to 2 to the right of x is equal to 2, you will not lift your pen. Therefore, the function is continuous at x is equal to 2. So let's take a look at the graph. May erase. So So 2 is here, right here. So from the left of 2, going to the right of 2. So you need not lift your pen. So at this certain point right here, the function is continuous, okay? So yeah, therefore the function h is continuous at x is equal to 2, but not at x is equal to 0. So now, what if, or suppose we are not given the graph of a function, but just the function itself. How do we determine if the function is continuous at a given number? So in this case, we have to check 3 conditions, okay? Take note of these. So the 3 conditions of continuity. A function f of x is said to be continuous at x is equal to c if the following 3 conditions are satisfied. And I know, I'm quite sure that you already know or are familiar with how we deal with the following. So letter A, or the first one, f of x, I'm sorry, f of c exists. Meaning, if you substitute if you evaluate the function at c, the value that you will be getting exists, is a real number. Now, for the second one, the limit of the function as x approaches c also exists. So it's not b and e. So it should exist. It should be the same for both the left and the right side. Now, for the third condition, so we need to make sure that the value of the function at c and the limit of the function as x approaches c are the same or are equal. Okay? So if at least one of these conditions is not met, f is said to be discontinuous at x is equal to c. So for us to prove its continuity, we need to prove uh, all 3 conditions. But we only need one condition to not be met for the function to be discontinuous. Okay? So now we proceed with example number 5. Determine if the function f of x is equal to x cubed plus x squared minus 2 is continuous or not at x is equal to 1. So we have to check the 3 conditions for continuity of a function. First condition. So simply evaluate or substitute. If x is equal to 1, then f of 1 is 0. So solving for that, that's f of 1 is equal to 1 cubed plus 1 squared minus 2. Wait. Erase minus 2. So that's 1 plus 1 minus 2. So that is 0 right there. For the second condition, that's the limit of the function as x approaches 1. So we can use the limit theorems for this example. So substituting for the first term, the second term, and the limit of the constant is the constant itself. So we will get 0. So that satisfies our second condition. Now, third condition, since the value of the function at c and the limit of the function are the same or are equal. So therefore, the function is continuous at x is equal to 1. Okay, very, very, very easy, guys. Example number 6. So determine if the function or f of x equals x squared minus x minus 2 over x minus 2 is continuous or not at x is equal to 0. So we still do the same thing. We need to satisfy the 3 conditions. So we have to check the 3 conditions for continuity of a function. Number 1, if x is equal to 0, so substituting I'm sorry. That's f of 0 is equal to 0 squared minus 0 minus 2 over 0 minus 2. That's 0, that's 0. We're left with negative 2 in our numerator. We're left with negative 2 in our denominator. So that will give us 1. For the second, so 1 is a real number. F of c exists. For number 2, the limit of the function. So again, we can use the limit theorems. We can use substitution and the constant rule. So that's 0, still 0. I'm sorry, wait. Yeah, we can use the limit theorems for this example. So in the end, we are left with, or our final answer is 1, and the limit exists. Number 3, since we were able to solve that earlier, f of c and the limit of the function as x approaches c are both 1 and are equal. So therefore, the function is continuous at x is equal to 0. Okay. So example number 7. Determine if the function is continuous or not at x is equal to 2. So solution. Note that if x, note that the function is not defined at x is equal to 2, since 2 is not in the domain of the function. Hence, the first condition in the definition of a continuous function is not satisfied. Therefore, f is discontinuous at x is equal to 2. Why? For the first condition, f of c. So if we have f of 2 right there, if we substitute 2 to our denominator, that's 2 minus 2, and that's 0. And again, whenever the denominator is 0, meaning the function is undefined, meaning f of c does not exist. So therefore, from the first condition being not met, the function is discontinuous at this certain point, x is equal to 2. Example number 8. We have here a piecewise function. Determine if the function is continuous at x is equal to 4. So this example was given in topic 1.1, so in our previous discussions. So solution. Note that f is defined at x is equal to 4. So x is equal to 4 belongs here because the condition is x is greater than or equal to 4. So, and that's 3 because if we substitute 4 here, that's 4 minus 4 squared plus 3. Of course, that's 0. So we will be left with 3. However, the limit of the function as x approaches 4 from the left. So here, from the left, if we substitute 4 here, because that's on the left side, because x is lesser than 4. So the limit is 5. While for the right side, that's 3. So therefore, the limit does not exist because it's different for the left and the right side. And so the function is discontinuous at x is equal to 4. So like we have here solved examples. Example 1, consider the graph. The function is continuous at x is equal to 0 because we can trace the graph from the left of 1 and from the right of 1 without lifting the pen. So if you're from the left side going to the right side going to the left side, both are continuous. So we have here another example. You see this point right here, that's not included. So at a certain point, x is equal to 2. The function is discontinuous at that certain point. So here, another one, the function values from the left of -2. What's the question? So consider the graph. Okay. So the function values from the left of -2 to positive infinity. So from here, going there, while from the left, they approach negative infinity. So it's going down. So therefore, h of x is discontinuous at this certain point right here at x is equal to -2. But if we consider x is equal to 0, which is right here, so we can draw our graph continuously. So therefore, the function is continuous at x is equal to 0, but not at x is equal to -2. Okay. Number 5, so for this function, again, we need to make sure that all the three conditions are satisfied for us to know if the function is continuous at that certain point. So yeah, you can actually study the solved examples. You can try to solve the examples on your own for you to better understand the topic by practicing on your own. Okay. So we now proceed to the second part of the discussion, which is a continuity on an interval. Earlier, it was a continuity at a certain point, but now we are concerned with continuity on an interval. So as an introduction, a function can be continuous on an interval. This simply means that it's continuous at every point on that certain interval. So let's say we have the number line. We have 0 right here. We have 1, 2, 3, 4, 5. So a certain function, let's say, can be continuous from 2 to 4 only, okay, at that certain interval. So equivalently, if you're able to draw the entire graph of the function on an interval without lifting our tracing pen or our graphing pen, or without being interrupted by a hole in the middle of the graph, then we can conclude that the function is continuous on that certain interval. So we begin our discussion with two concepts which are important in determining whether a function is continuous at the endpoints of closed intervals. So for one-sided continuity, a function f is said to be continuous from the left at x is equal to c if f of c, if you evaluate the function at c, is equal to the limit of the function as x approaches c from the left. So again, if you have the negative sign right here, that means that's from the left side. For the second one, a function f is said to be continuous from the right at x is equal to c if f of c is equal to the limit of f of x as x approaches c from the right. So here are known facts on continuities of functions on intervals. So continuity of polynomial, absolute value, rational, and square root functions. Number 1, polynomials are continuous everywhere on every point on every interval because there are no restrictions for polynomial functions. Number 2, the absolute value function f of x is equal to the absolute value of x is also continuous everywhere. Same with polynomial functions. Okay. Number 3, rational functions are continuous only on their respective domain. So as long as it does not make the function undefined, so at that certain point, the function is continuous. But if that certain value makes the function undefined, so at that certain point, the function is discontinuous. Number 4, the square root function f of x is equal to the square root of x is continuous on 0 to positive infinity. So of course, because we cannot extract the square root rather, of negative numbers because that will result to an imaginary number. So its domain is only from 0 included, to positive infinity. By the way, if you see the symbol, so that means that at that certain point, it's included, but you see that one, meaning that's simply the boundary. So limits and continuity on an interval. We first look at graphs and functions to illustrate this type of continuity. So same with earlier. So given the graph of the function, so using the given graph, determine if the function f is continuous in the following intervals. So first one is -1 to 1. So -1 is right here, 1 is right here. Okay. Negative infinity to 0. So negative infinity from here going to 0 there. Okay. Then 0 here going to positive infinity. So solution, remember that when we say trace from the right side of x is equal to c, we are tracing not from x is equal to c on the x-axis, but from the point c, f of c along the graph, okay? So number one, we can trace, the graph from the right side of right side of x is equal to -1 to the left side of x equals 1 without lifting the pen we are using. Hence, we can say that the function f is continuous on the interval -1 to 1. So again, -1 is right here, 1 is right here. So from here, going here, okay? At that certain interval, our function is continuous. Actually, this topic is very, very easy. So number 2, so if we trace the graph from any negatively large number up to the left side of 0, we will not lift our pen. So from negative infinity, let's say down here, from here, going there, going to the 0. So we need not lift our pen. So the function is continuous at negative infinity. And lastly, from 0 going to positive, 0 going to positive infinity. And then, so we need not lift our pen as well. So for the second interval, so from negative infinity to 0, f is continuous. So also for the interval 0 to positive infinity, the function is also continuous. So another one, consider the graph. It's still a parabola. So determine using the given graph if the function is continuous on the following intervals. So a, that's -1 to 1. Then b, that's 0.5 up to 2. So for letter A, again, -1 is right here. 1 is right here. So if we draw our graph, we need to stop at 0 since we need to draw this circle right there, meaning that's not included. Then we go back going to 1. So if we trace the graph of the function h from the right side of f of x is equal to -1 to the left side of x is equal to 1, we will be interrupted by a hole when we reach x is equal to 0. Okay, same with what I have showed you. So we are forced to lift our pen just before we reach x is equal to 0 to indicate that h is not defined at x is equal to 0 and continue tracing again starting from the right of x is equal to 0. So therefore, we are not able to trace the graph of h on -1 to 1 without lifting our pen. Thus, the function is not continuous on -1 to 1, of course. Now for letter B. So that's 0.5. 0.5 is right here, going to 2. So from here, going here, what do you think? Is it continuous or not? The answer is very obvious. So for the interval, closed interval, 0.5 to 2, if we trace the graph from x is equal to 0.5 to x is equal to 2, we do not have to lift the pen at all. Thus, the function h is continuous on the closed interval 0.5 to 2. So now, if a function is given without its corresponding graph, same with earlier, we must find other means to determine if the function is continuous or not on an interval. So here are definitions that will help us. So a function f is said to be continuous. 1, everywhere if the function is continuous at every real number. So in this case, we also say the function is continuous on every element on the set of real numbers. So the symbol right here that indicates or that means the set of real number. Number 2, on an open interval AB, if the function is continuous at every point in that certain interval. So it's continuous if you need not lift your pen on that certain interval. Number 3, on A to B, here A is included, that's closed on A. If the function is continuous on A to B, and from the right at A. So meaning, if this is A, this is B. So it should be continuous going there, but A is included. Okay. Number 4, on A going to B, A to B, B is included, that's closed in B. If the function is continuous on A to B and from the left at B. So from here, going here, but B is included. On the closed interval A to B, if the function is continuous on both A to B and on A to B. So meaning A and B are both included. Okay. Number 6, on A to positive infinity, if the function is continuous at x greater than A. So meaning from A going to positive infinity. Okay. Number 7, on A to positive infinity, if the function is continuous on A going to positive infinity and from the right at A. So still the same thing with number 6, but for number 7, A is included. Number 8, on negative infinity going to B, if B is continuous at all x lesser than B. Okay. Number 9, on negative infinity to B, if the function is continuous on negative infinity to B and from the left at B. So the only difference for number 8 and 9 is that for number 9, we have a closed interval, meaning B is included. Okay. So we have example 3. Determine the largest interval over which the function f of x is equal to the square root of x plus 2 is continuous. So for our solution, observe that the function f of x is equal to the square root of x plus 2 has function values only if x plus 2 is greater than or equal to 0. Again, for radical functions, the value should not be lesser than 0. It should not be negative because we will be left with imaginary numbers. So for us to have real numbers, we need to make sure the value is 0 up to positive infinity. So that is if x is an element of the set of numbers -2 to positive infinity. 2, -2 is included. So for all values of c, which is an element of -2 to positive infinity. So f of c is equal to the square root of c plus 2 is equal to the limit of the function x square root of x plus 2 as x approaches c. So moreover, f the function is continuous from the right at -2 because you solve for f of -2 and the limit of the function that will be equal. So therefore, for all x, which is an element of the set of numbers -2 to positive infinity, the function is continuous. So to put it simply, the largest interval should be the certain interval wherein our function will be defined or our function will result to real numbers. So it so happens that this is enclosed in a radical. So we need to make sure that the resulting value will be a real number and not an imaginary number. So we need to make sure that the least value that we can substitute here should make the function or should make the function equal to 0, which is -2. We cannot have or let x be equal to -3, -4, -5, because if it happens that this is -3, that will give us -1, and that will be an imaginary number. So it should be -2 up to positive infinity. Okay. At negative infinity, it's an open interval because it's increasing. We do not know what is our largest number so far. And here, of course, -2 is included. Okay. Example 4, determine the largest interval over which h of x or the function equals x over x squared minus 1 is continuous. So observe that the given rational function is not defined at x is equal to 1 and x is equal to -1. So it will not be defined on those certain points, because if x squared or if x is 1, our function will be undefined. If x is equal to -1, our function will still be undefined. So hence, the domain of the function h is a set of real numbers excluding -1 and 1. So as mentioned at the start of this topic, a rational function is continuous in its domain. So hence, it is continuous again over all real numbers. Okay, all real numbers except -1 and 1, because those are the only points wherein the function will not be defined. I hope that's clear. So example 5. So consider the function, the piecewise function, g of x. So is g continuous on first 0 to 1? 1 is included, and on 4 to positive infinity. So solution, since g is a piecewise function, we just look at the piece of the function corresponding to the interval specified. So for number 1, on the interval 0 to 1, close interval to 1, g of x takes the constant value 3. So 0 to 1, it's where? 0 to 1 here. There. So the value of the function from 0 to 1 is 3. Okay, and also for all c, which is an element of 0 to 1, the limit of the function as x approaches c is 3, because the limit of a constant is a constant. So it satisfies our condition. So thus G is continuous on 0 to 1 closed interval. Number 2, for all x greater than 4, it should be here, this one. So the corresponding piece of G is G of x equal to x minus 3. Again, this one right here, which is a polynomial function. And recall by the rules that a polynomial function is continuous everywhere in the set of real numbers. So hence, the function is surely continuous at this certain interval. Okay, remember that rule that a polynomial function is continuous everywhere. It has no restrictions, but make sure that it's under the set of real numbers. So below, we have the solved examples. Again, you can try to work on these examples on your own, try to study, try to solve the problems on your own for you to be able to practice and understand the concepts and the topics better. So that's it for my discussion on continuity of functions. If you have questions, clarifications, again, you're always free to ask. Thank you so much for your time and for listening. You take care always. Bye-bye for now.